In this problem, we're asked to integrate the following. We're going to use integration by substitution. And in the very first one, we notice that the top is the derivative of the bottom. So if we take the derivative of 2x squared minus 17x plus 9, we get the top. So we're going to let u equal 2x squared minus 17x plus 9. So that means du is going to equal 4x minus 17 dx. And now I can make my substitution. So what I have here in this equation is, well, first of all, I've got, if I treat this as two separate factors, to make it a little bit easier to see that I've got exactly what I need, times 4x minus 7 dx. Because keep in mind, this is all over 1, so all I've really done here is now I can see that this, oh yeah, is 1 over u. Times, well, this whole bit here is du, so I can write 1 over u du. The integral rule for 1 over u is that this function has to be, the derivative of natural log of u is precisely what gives me 1 over u. So I have the natural log of the absolute value of u plus c. Substitute my u back in, so ln of 2x squared minus 17x plus 9 plus c. In the second one, I've got a similar situation. Again, I'm going to let the this integral sign should actually be right there. So in this problem, we have the integral of this whole mess, and so we're going to let u equal x to the third minus 5x squared plus 1. So that means du is going to be 3x squared minus 10x dx. So that's the whole thing I have there. And now I'm going to go ahead and make my substitution. Again, in a similar fashion, I can split this up into 1 over x to the third minus 5x squared plus 1 times 3x squared minus 10x dx. This guy is my du, and this is 1 over u, so I have 1 over u du, and the integral of that is similarly the natural log of u plus c. Substituting my u back in, I have the natural log of x to the third minus 5x squared plus 1, close the absolute value sign, plus c. Now the final problem can be a little bit tricky at first because at first it's not obvious what we should do. So the problem here is actually a problem related to using our knowledge of natural logs. So we notice that we have the natural log of x squared. But this is really a composition of functions. So to take the derivative of this, it would actually require the chain rule and would not necessarily produce what we want. So if I write this as the natural log of x squared times 1 over x dx, well, we know that the derivative of ln of x to the first power is 1 over x. But we don't know exactly what the derivative of the natural log of x squared is. So what I'm going to use is a property of logs. And that property says that basically if I have the log, it could be natural log or any other base. I'll just go ahead and write this in terms of natural log. If I have the natural log of a raised to the m power, then this property says I can bring the exponent out front as a factor instead of as an exponent. This could become m times the log of a. So in this case, I'm going to do that. I'm going to bring the 2 down. I have the natural log of x times 1 over x dx. So what I can do, now that I was able to take care of that 2, I can just factor that out and write it like this. So this is much easier now because now I can say, well, hey, u equals the natural log of x, du equals 1 over x dx, and I've got exactly what I need. Here's my du, here's my u, and so my problem simply becomes 2 times the integral of u du, and the integral of that is equal to 2 times u squared over 2 plus c. These guys cancel, and so now I just have u squared plus c. Replacing my u back in, I have the natural log of x squared plus c.